Hello, February 9th, Tuesday of 2024. Yesterday I was able to solve problem 15, so maybe we could get started on problem 16. Now, the first one is easy. One disregards the constant. So that's it. That was this guy. Next, we must express it in terms of the zeta function. All sums going from n equals 1 to infinity. And I think we need the real part of s to be larger than unity here. The first idea is to prime factor n, and then for each prime factor, we know p to k's, it's, I need to find that out, but it's a known relation. And then, but then we are already on the way to writing the Euler product. On the other hand, every n has divisor unity. And then for each divisor, you see, the idea is to take out all divisors of n and then add them up. So I'll just set k equals to 2, and then I'll write it up by hand. So it's 1 to minus s plus 1 plus 2 to 2 minus s plus 1 plus 3, 3 minus s plus, 1 plus 2 plus 4, 4 minus s, and then 6, that's 1 plus 2 plus 3 plus 6, 6 to minus s, etc. So first it's the sum of n to minus s plus, and then all the even ones they become blue. They have a divisor 2. And then it's all the even ones. And then all the multiples of 3. You see? We call it d from 1 to infinity. D theta of oops. Now summing over these, I thought I could express that in terms of the zeta function. Well, we just take 2 to minus s outside. So it's d to 1 minus s. So d itself, and then d to 1 minus s, zeta of n, nope, zeta of s, of course. Don't let yourself be confused. And then this sum oh, zeta of s minus 1. Shocking. And the generalization we just put k minus 1 up here. So it's difficult for you to read. I'll make it red as well. So it's k minus 1, k minus 1. So instead of unity, we get k minus 1. And that means it's s plus 1 minus k in general. that's a surprise. And you know what? Can we check it? Oh yeah, we can compute the zeta function generally. So I will just check that numerically before continuing. I've had my lunch and done my programming. So I defined the function LF. And it makes a list first of LS and then of the product of the zeta functions. And I computed it for k equals 1, 2, 3, and 4 for various values of s. I don't know why I put an imaginary. I don't think that's necessary. Let's try it without it afterwards. And you see the two numbers here. They agree pretty well. These as well. And these. So that's pretty good. So let's try it without the imaginary part here. See what happens. Well, that agrees even better. Lovely. So that is a vindication of my formula here. All right, next the Euler product. It is a multiplicative function, but it only holds if they are mutually prime, because then the divisors can be multiplied to get a divisor of a times b. So it's not strictly multiplicative. So my first idea to get 1 minus p to k minus 1 minus s of p times p to minus s, but I don't think this is sigma of k to minus 1 of 2p of p squared, that should be, times p to minus 2s, that's fine. But I don't think this is. I think this is the general formula. Now, what am I writing here? Kth power of the divisor. So it's 1 to k, 1 to k. So it's p to 3k divided by p to kth minus 1. well, not even this. That's p plus 1. Oh yes, it should be p plus 1, of course. P to k is plus 1. I'll just correct that. Now, I think it's better to start from the other side. Just like we did up here. And let's just take 2, the prime factor of 2. So k minus 1, we don't want to write it every time, so we write L. And that needed to come from 1 minus something 2 to minus s. And what can this something be? They just say, write like it should be nothing special, something you are able to do once you've seen this. Well, this is not a power function, so I don't see how we can write it like this. And that comes from the fact that it's not absolutely multiplicative like the characters are. I have no ideas at the present, so I'll just stop. I just looked up the definition of an Euler product. This is actually the Euler product. And it can only be written in the form we already know when A is totally multiplicative. Which means that I actually did solve the problem. I just didn't know it. So LF of S equals the product over all primes the sum n equals 1 to infinity, p to naught to infinity, p to n plus 1 minus 1 divided by p minus 1 to p to minus n s. I would guess and see that this chi of n just needed to be put up here. Chi to p of n, so that's chi to p. So I just think we just put it on here, chi to p. Yeah. Can't see the problem. Maybe I should just write it. Yeah. That's it.